Hi, and welcome to S for Science. Matter. Many things around us are made of matter: air, water, the grass. And matter is mostly made of atoms. And this is the atomium. It represents an iron crystal magnified 165 billion times. Each sphere represents an atom. This may look like a very large increase. So, to put it into perspective, if this figure were increased 160 billion times, it would occupy the volume that all the water on Earth occupies. This may make you think that you have many atoms in your body, and it really is so. But atoms only represent 4% of everything in the universe. What about the other 96%? Surely you have already thought of dark matter and dark energy, these commonly mentioned names when talking about the universe. Actually today, although we know almost nothing about these two things, we firmly believe that they make up 96% of all matter and energy in the universe. So it could be said that we only know 4% of it. But little by little, we will know more about that mysterious and significant 96%. Dark matter, dark energy. Why do they both have this adjective? Well, basically because neither of them emits or absorbs electromagnetic radiation. In other words, they cannot be seen. And this is the main problem. It is difficult to understand the nature of something that you cannot even see. Something very important to understand is that dark matter and dark energy are two completely different things that have nothing to do with each other. Both are invisible, yes, but their existence has been deduced from things that have nothing to do with each other. And of course, they have nothing to do with antimatter. So let's start with dark matter. It is calculated that dark matter represents 23% of all the mass energy in the universe, almost a quarter. The question that you're asking yourself is possibly how can we believe that something exists in the universe that represents no less than 23% of it without ever having seen it? And yes, it is a bit counterintuitive, but in reality, we have observed some phenomena in the universe. I am simply going to summarize them in three that cannot be explained unless dark matter is used. The first evidence is gravitational lenses. There are a large number of areas in the universe where, if we focus our telescopes, we can see how the light that comes from the universe is curved, in such a way that the galaxies and stars that emitted this light look deformed. This is an effect of gravity, or what is the same, of the deformation of space-time. What you're saying now is a scheme of how this effect, which is called gravitational lens, works. It's somewhat complicated to understand, so instead take a look at this simulation that represents a galaxy passing behind a black hole. These massive objects distort space-time a lot. Their gravitational field is very powerful, which causes a strong gravitational lensing effect. One would expect to find gravitational lensing in very massive places in the universe, like for example around the black holes. However, gravitational lenses have been found from places where apparently there was nothing. This is how we see the cluster of galaxies Abell 1689. It's beautiful, right? But look closely at the image. Don't you see small bright lines all oriented circularly around nothing? Here you're looking at dark matter. Like normal matter, dark matter also has gravity as an intrinsic property, cause of this enormous deformation of space-time. It is calculated that in this area of the universe, the amount of dark matter is equivalent to 10 to the power of 14 suns, which causes this enormous deformation. The second piece of evidence of the existence of dark matter is the speed of rotation of galaxies. As it could be expected, the stars and dust located in the surroundings of the galaxy, that is to say, in the outmost parts, should rotate more slowly than the stars and dust that are in the most central parts. And this doesn't happen. In our own galaxy, the Milky Way, it is observed that all stars rotate at approximately the same speed. And this wouldn't make sense unless we resort to our friend. Yes, it is calculated that there is a cloud of dark matter 9 times more massive than our galaxy, responsible for its rotation being much more uniform. Given that by adding so much mass to the galaxy, it just becomes the small center of a massive area of the universe. What you're seeing now is a representation of the system, with dark matter in the form of a blue haze around our galaxy. The third piece of evidence is closely related to the second one, and it basically says that galaxies shouldn't exist if we only take into account normal matter. Basically because galaxies can't exert enough gravity on themselves to hold their stars in such a way that the stars should shoot out into intergalactic space. But why doesn't this happen? Because there's something that causes gravity to be so much greater. We are immersed in that something that surrounds the entire galaxy, and that something is that cloud of dark matter, a large amount of matter that creates the necessary gravity as for our galaxy to exist. This implies that the Milky Way is surrounded by a lot of dark matter, but really it is not only surrounded, but also immersed in dark matter. And in the same way, so is the solar system, and the place where you are. And in fact, you're being hit right now by many particles of dark matter. And yet we are unable to detect it. We know it's there, we know it must exist, but for some reason we can't detect it. Something fascinating, but at the same time a bit creepy. Now we know why we believe dark matter exists. Its existence is essential to be able to understand certain phenomena that occur in our universe. But what is dark matter made of? It is important to understand that although it has a name very similar to the normal matter that we know, this one is made of atoms, while dark matter has a very different composition. Many candidates have been proposed as components of dark matter, being most of them hypothetical subatomic particles, such as axions or WIMPs, that despite their name, they are not funny. It has been calculated that if WIMPs are the constituents of dark matter, 100,000 trillion of these particles per second would go through every kilogram of your body. The problem here is that these particles are very elusive. Have been and are being carried out many experiments that are trying to detect them, but so far, none have been successful. Sometimes observations are made that seem to indicate that dark matter has indeed been detected, but they are not the definitive proof. And in the same way, a lot of evidence also emerges that rules out the existence of the proposed candidates, but without being able to be confirmed. So the investigation continues, and from the data that is being obtained, new detectors are being built, testing new methods. Time will end up giving us the true candidate. Now we know what dark matter is. Well, actually, we know why its existence is necessary, and we know that attempts are being made to find out its composition. But there's still 73% of the universe. Dark energy. Even more mysterious than dark matter, little is known about this form of energy that permeates the entire universe. Roughly, what we know about dark energy is that it has a very low density and that it is present in all places of the universe. It permeates space-time, being equally present in all places. Yes, dark matter is also inside you, and inside and outside of anything. It is to blame for the universe being in accelerated expansion. This makes it that unlike dark matter, which is quite harmless, dark energy is one of the main enemies of the universe, although we could also owe our existence to it. This is the density of dark matter, 10 to the negative 29th power per cubic centimeter. It seems impossible for something with such a low density to be the largest component of the universe. But think for a moment that it is everywhere in the universe, absolutely everywhere. And it is this low density that makes it so difficult to detect dark energy. Then how do we know it exists? In 1998, observers at the Lawrence Berkeley National Laboratory discovered something that would change our understanding of the universe. They realized that the light emitted by distant galaxies had something called a redshift that increased more and more. But what is this redshift? Well, basically, it is a shift of the light that comes from distant places in the universe towards red light. So that you understand, the photons that can come out of a star can have a certain wave frequency. This wave frequency, when redshifting, presents an increasingly reddish color. There are different causes that can cause redshifting. One of them is the displacement between two bodies. Imagine that you have two bodies. One of them is an emitter of light and the other one an observer. The observer can be the Earth, for example. Now imagine a photon that's coming out of this star and going towards the Earth. This photon will have a certain frequency, but this frequency will not be measured in the same way if the Earth is still or if the Earth is moving. If the Earth is moving, the frequency of this photon will be different from what would have been perceived if the frequency were received on an Earth that was still relative to the light source. This is why some frequencies, when they reach the Earth, present a redshift, since when coming from that star, its frequency has been slightly shifted towards red due to the fact that the stars and the planet in question are moving away. This is what causes some stars to have more of a reddish color than they should have, what is called the redshift. But there are other more interesting causes for what concerns us. Another more interesting thing that causes the redshift is the expansion of spacetime. Imagine that this represents the wave of a photon that travels from one point to another in the universe. This photon has its wavelength, that is, the distance between two crests. The wavelength will determine what color this photon will be. But what happens if we expand spacetime? This happens. The wavelength increases, so the color of the photon tends to get closer to red. This is currently one of the most compelling proofs that confirm that the universe is really expanding. But what they discovered in that observatory in 1998 wasn't that. That was already known. What they discovered is that this expansion, this dilation, let's say, between two wave crests is getting faster. And this is why the speed of expansion of space-time is getting faster. This discovery meant something totally unexpected, given that to date, it was believed that although the universe was expanding, it would end up reversing due to the gravitational attraction exerted by matter to itself, making the universe contract, culminating in its entirety at the end of its existence at the same point, what is called the Big Crunch theory. However, the fact that the expansion speed is increasing implies that the distances between galaxies in the universe will be bigger and bigger, until one day in the far future it will be impossible to see any galaxy from any other, until reaching a point in which all the atoms are separated from each other by enormous unimaginable distances. All the energy and the matter will be destroyed, remaining in the universe only the remnant radiation of the last subatomic particles, something that will happen in about 20 billion years. A theory of the end of the universe that is currently one of the most supported. And this theory is known as the Big Rip. And who is guilty for this expansion? Dark energy. It is known that it exerts a negative pressure on the universe, which causes its expansion to slow down faster and faster. Dark energy is nothing more than the result of the need to understand why the expansion of the universe is getting faster and faster. Dark energy could have made the universe a place suitable for life long ago, but it may also end with it. So dark energy may end with the universe. This will basically depend on how much dark energy exists. If there is too much, our universe will end up in a big rip. If there is not enough, it is believed that there will come to a point where it will begin to contract again, something that is currently believed to be unlikely. It will depend on whether gravity is strong enough, and this will largely depend on whether there is enough dark matter to exert enough force. And in this scenario of great forces disputing the future of everything, we're only the 4% remaining of a universe with a 96% in constant battle. A 4% that the only thing that seems to be able to do is act as a simple spectator. A simple spectator who tries to understand this vast universe. After all, we're nothing more than atoms trying to understand themselves. Well, and the other 96% too. We are a 4% which, however insignificant, it may end up being decisive. Thank you very much for watching the video, and goodbye.